And I don't know. I think next year I'll restructure the lesson. Today it seemed pretty dragged out, and I don't recall that being the case last year. But still, you guys had to deal with it. Um, Here's what you were supposed to be able to do, and we covered almost all of it. And especially with you guys being math lab, and we did that extra lesson in math lab, you have covered all of it at some point. So we were looking at associations and categorical data for the first part. So if you calculate some relative frequencies and see that there's a significant difference between them, then there's probably an association there. Doesn't mean that one caused the other. They could be completely unrelated things, like left or right-handed people and what dessert they prefer. We know that those don't have a relationship at all, but if we calculate the relative frequencies and it's like a 10-90 split, then we would say, yeah, there's an association there, even though like there's definitely no cause, if that makes sense. So keep that in mind as you're doing your practice. Look at those relative frequencies. If it's not close to 50-50, then there is technically an association there. Be able to calculate relative frequencies. That was more so the task from yesterday, but you saw it again today. So use that to support your answers. And then the back of your notes was us plotting some data, putting a line of best fit, and then using that to create a linear model. When you hear the word linear, what should you automatically be thinking of? Straight line. And what's our formula for straight lines? Y equals mx plus b. So that's why one of our learning targets mentioned something about describing our rate of change and describing our y-intercept in everyday language. We didn't really get to the everyday language part. But rate of change is another word for what? Good, slope, rise over run. We also learned the new equation to calculate it. That, whatever situation is going on, like in our case, we talked about the oranges, and we had a equation pretty similar to this. You need to be able to tell me what that 0.22 is representing. You need to be able to tell me what that 0.5 represents. Okay, and we didn't talk about that, so maybe let's talk about that now. And I'm going to use, this is our linear model, but I'm going to use the one that they created with technology, which is this one, which our answer was close to it. So today we just estimated it. In a different lesson, I'll show you how to create this with technology. But remind me, the slope is what? Like what formula? Well, that slope intercept form, what about just the slope? Maybe the easier one that we've done before this unit. Okay. So slope is rise over run. So rise would be your y-axis, right? So my change in y is having to do with my weight in kilograms. Over my run, so my x-axis, what is my x-axis representing? So if this is my slope, 0.216, and it is a decimal, it is a fraction, but for this purpose, let's put it over 1. This is how many kilograms it is changing on average for every 1 orange. Does that mean that every orange weighs 0.216 kilograms? No. As you saw in the video, some of the oranges were really big, some were really small. But on average, that's what it's changing by each time. So that's what you would say in everyday language. For your y-intercepts, So wherever it touches here on your graph, according to this, it touches like about right here. That coordinate would be 0.345 for my y-intercept. 0 oranges, the weight is 0.345 kilograms. Why does that happen? Why is there still weight even when there's no oranges? What were they still putting on that scale? A box. And I don't have the video of it anymore, but that is the weight of the box. That's when there's no oranges in the box. So that would be your everyday language. That is how much the box weighs. And so forth. Whatever random situation it's giving you, that's how you say it in everyday language. What's my y-axis say? Over my x-axis, rise over red. Y-intercept is when x is 0. So whatever the x-axis says would be 0. The y-axis would be what it is. Okay, so that's what I mean by everyday language. You'll have some questions on your test, just like. All right, but other than that, well, we didn't really talk about that, but that was something that you were supposed to see. You need to be able to draw a linear model. So put a line through the middle of your data where all the points seem to be clustered around it. We practiced that in math lab right before we started this unit. Hopefully that makes sense. You have 2 assignments to get 80% or higher on, and then you could go back and do whatever you prefer. Ideally, it would be making sure that your lesson 1 and 2 are already finished, or IXL skills. But these need to be done at 80% or higher. Don't just get the answers from your friends. That really does nothing for you. Any questions so far right now? Okay, so then you have time to work on these 2 things. Would like help with lesson 4, number 3. We're doing that right now. And a taxi driver records the time required to complete various trips and the distance for each trip. The best fit line is given by this equation. Why they have it twice, I think, is just a typo. But y represents the distance in miles and x represents the time for the trip in minutes. Even if they didn't define that, hopefully you can tell from the x and y axis. But we're gonna answer these questions using the best fit line. The distance for a trip that takes 20 minutes is about blank miles. And using the best fit line, the time for a trip that is 6 miles long is approximately blank minutes. So it's all about just knowing where to plug in. So if this is my equation for my linear model, and we want to find the distance is x or y. The y, it says right here, and it's also the y-axis on your graph. So the y is going to be our unknown. That's what we're going to be solving for. And they're giving us this value, which is time in minutes. That's going to go in place for the x. So plugging in a 20 for the x. You could also, I guess, try to find it on the graph, but with these decimals, it's going to want exact answers. So I'm going to put that in my calculator to get that exact answer. Right, so me plugging in 20, I get this value for the y, and it said round to the nearest end. So anytime I get a decimal that I need to type in, I always check if there's any round equals. The 10th spot is how many decimal places? Right, no one? What's the 10th spot? Okay, so we're basically rounding to the first decimal point. Wherever you need to round to, underline it and then look to the right of that number. If that number is 0 through 4, then where you underline should stay the same. If it's 5 through 9, then where you underline needs to go up 1. So is my answer going to be 9.7 or 9.8? So 9.8 is what this box is. For the other answer, for the other one, it's giving us a different thing that we're solving for. We want to find the time. So what's going to be unknown is the x this time, since x this time. And they're giving us that the trip was 6 miles long. So where does that 6 need to be plugged into, the x or the y? For the y, because that's miles. If you look at your y-axis, that's where the miles were. So plug it in the correct spot. And then in this case, we're solving for the x. So isolate it, start with what's farther. What do I need to get rid of first? And how do I get rid of it? So we're gonna do that. And don't round early. Like wait to do your rounding at the very end. So in my calculator, I'm gonna do 6 minus 0.417. All right, and then so 5.583. Sorry, I would scroll, but it's not gonna make a difference. My writing is still gonna be at the bottom. All right, and then what's the opposite of multiplying by that decimal? So we're gonna now divide that on each side to get what x equals, our time. And then we'll round it to the nearest 10 after that. So take that value, divide it by 0.467. And now, again, like I said, save your rounding till the very end. If you round early, your answer will be off. So we're at the very end now. This is what x equals. We're rounding to the 10th spot. So underline it and then look to the right. Since that's a 5, will my answer end up being 11.9 or 12.0? 12.0 basically. When I round up 1, it brings it up. I don't know if they want a 12.0. I feel like they just want a 12, but I'll make sure it accepts both. And I'll print that right now. So linear models predict things that we didn't necessarily directly test. Oh, why does it say, I don't like the way it does that. Let me make sure it does all those other answers, because that's not rounded to the nearest 10th. Okay, so it definitely doesn't want a 12.0. I'll add it just in case. But I don't like that it counts the 10 as an answer because that's not rounded right. But yeah, for that one, the answers were 9.8 and 12. Questions on this one? Questions on others, if any? Dan?
Oh, same as me.
All right, so number 5 on lesson 4. All right, a random selection of indoor and outdoor pool managers are surveyed about the number of people in each age group that swim there. Here are the results. Based on the data, does there appear to be an association between the pool type and age group? Complete the following to explain why or why not. So before I do see that there's an association or not, I'm going to kind of read ahead to see what I should be dividing by. Because it probably wants like something about the relative frequency. So I'm going to kind of read ahead. It says about blank of the swimmers in the outdoor pools were younger. So let's look at the total for the outdoor pools. What do I get when I add that? And it says about blank of the swimmers in the outdoor pools were younger. So I'm going to take this value, divide it by my total outdoor pools, and see what percent that is. So 317 divided by 1669 and by 100%. I'm getting about 47%, which I don't think I saw that in my options. Oh, I know, over here. So yeah, that is one of my options. You have to know what to divide by. So it was basically saying of the outdoor pools, whatever follows the phrase of is usually your denominator. And they didn't give us the total, so you have to calculate it yourself. And then younger is that number, so 47%. Then it says, well, only about blank of the swimmers in indoor pools. So how many were for the indoor pools? What's the total for indoor pools? 204. So that's going to be my denominator, whatever follows the phrase of, like out of this many, is going to be my denominator. And we're younger. So between these two values, this would be the ones that were younger. When I divide that, 41 divided by 204, get a decimal, times it by 100%. That's about 20%. So while only about 20% of the swimmers in indoor pools were younger. So since there is a large difference in the percentages, it suggests that there is or is no association. There's a big difference in the percentages. Is there an association? Yeah, that's what we talked about today. So if it's like a big split versus like a 50-50 split, then there is probably an association. Remember, association is not necessarily like a cost. While these are completely, maybe not completely unrelated, but if there's a trend, then there is an association. So a big difference in the percentages. So then going back here, you'd say there does appear to be an association in variables. Right, let me make sure the key is completely right. It is. Right, questions on the one? Questions on others? Center? Number 4 on lesson. Okay, so different practice, lesson 3, number 4. We have several college students are surveyed about their college location and preferred locations for spring break. What percentage of people who prefer to spend spring break at the beach go to college away from the coast? And what percentage of people who prefer to spend spring break skiing go to college away from the coast? So notice our answers are percents. How do you get percents? So yeah, we're dealing with relative frequencies. To get a decimal or percent, you have to. So the hard part is knowing what to divide by, but hopefully you're paying attention to like those little tricks. When it says what percentage of whatever follows that phrase of is usually your denominator. So out of these people, among these people, given that, those are all different ways to say. So that's going to be my denominator. People who prefer to spend spring break at the beach. That would be me adding 37 plus 54. Get that total. Which is 91, by the way. And out of those people, we're trying to see how many go to a college away from the coast. So then reading these. So 54 would be away from the coast. So that is how I get what I need to divide by. 54 divided by 91. If I want a percent, times that long decimal by 100%. That most closely matches 59 or 60. Good. It's a long decimal. When I do it as a percent, it's this. Is that closer to 59 or 60%? Okay, good. That's in your rounding skills. So 59 should go there. Then it says what percentage of people who prefer to spend spring break skiing. So figure out how many people prefer to spend spring break skiing. What's 24 plus 36? That would be my denominator. So out of these many people, because remember your percent should never be over 100%. Out of those 60 people, how many go to college away from the coast? 36, and that's what I need to divide by 60. So don't get confused, like 36 is an answer option, but that doesn't mean that's this answer. That's just the people that meet that criteria. You still need to divide it by 60 to get that decimal, and then times it by 100% if you want the percent. So this one, the answer is 60. All right. Make sure the P is right. Oh yeah, that's how you do it. Oh, if someone has a question and it's really quick, you might be able to squeeze it in. Any others? Well, hopefully, I mean, maybe this isn't your cup of tea. Maybe you're not fascinated by statistics at all. But I don't think the calculations are hard. It's just a matter of knowing what to put in your calculator. What to put in. So anything that follows the phrase of should be your denominator.